So here's an example of a multiscale multi-material simulation. We have here is a pressure vessel that has a continuous fiber composite. You see the different loadings and the different microstructures. So on the top right, this is the continuous fiber composite. Here we have a chopped fiber composite that represents the boss region. And here we have a porous adhesive that is gluing those two together. So you show how they're both all simultaneously running and the different loadings that are being transferred to the different materials. The next stage, I'm gonna walk through and just walk you through how to create a microstructure by going through these three different microstructures and take you from just simply creating a basic microstructure to adding more intricate material properties and damage criteria. So this will be our first example that we'll walk through today. And what this is a chopped fiber RVE. So we first do is you open Multimechanics or the MultiMech tool. We have the GUI, and the GUI is separated by three different segments. We have the geometry, where we create the microstructure and all the geometries and create the appropriate sections. We have the materials tab, where we can create a wide variety of materials and designate that to the region that was created, and then conditions, where we control boundary conditions and loadings and virtual tests. First, I'll go through how to create a microstructure. Select Undefined Microstructure, and here we'll bring up the microstructure generation box. Here we have a lot of different inclusions we can decide from, but if we want to do chopped fiber, we go cylinder. We have the option of having spherical, ellipsoidal, irregular, and we even have a weave builder that can do bidirectional woven composites. After selecting cylinder, we decide pick a volume fraction that we'd like, and if you want to have a continuous fiber composite, you can select this, but in this case it's chopped, it's discontinuous, so we'll unselect it. And we select the diameter of the fibers, which you can have a range of which, and also a range of lengths of your fiber. The orientation, we have a few different options. One is random, where the fibers, as it seems, are randomly distributed throughout the RVE. Unidirectional, where all of the fibers are aligned in one direction. Normal distribution, whereas you pick an average vector in which they're all directed, and then have a certain variation in the different directions. And then also you have tensor, which is a more complicated fiber orientation input that can be used from, say, different tools like Moldex and Moldflow. In this case, we'll go to normal distribution, where we align all the fibers in the X direction and vary them in the Y and Z directions. You can put in the sample dimensions. You can make your RV as large or as small as you want. You can do sensitivity studies on the convergence of different sized representative volume elements. After you select the mesh refinement, you can go and create your microstructure right here. It'll bring up a Gmesh window where you can observe the microstructure you just created and go back to this dialog box and make any changes you want. But once you're done, you select Apply. Sure. We'll go into the materials box next. This is where we create our materials. See here, I have a couple materials created. So for the fiber, we have a lot of different options. We can choose to represent our material. In this case, we have a carbon fiber, so we'll represent it through an orthotropic linear elastic material. Here you have all the different engineering constants you can input for that. Once that's all filled out, select OK, and go to the matrix. In this case, we'll do an isotropic linear elastic material. Once you're done filling all this out, you go to the regions, and from the microstructure generation tool, the regions are automatically made. And so you have the matrix, and you assign the matrix material to the matrix region, the fiber to the inclusion region. After you're done creating and designating your materials to their appropriate regions, go to Conditions tab, and you can pick your local boundary condition. What local boundary condition is, it's a way for MultiMech to govern how the loads are transferred to the local microstructure. In this case, a planar displacement boundary condition works great. So in this case, when I select Run, it'll actually homogenize. And what it does, it takes the homogeneous properties and all the orthotropic directions. Once you select that, it'll quickly output your results, seen here. So you see we have the modulus in the 1, 1 direction, 2, 2, 3, 3, and you have your Poisson ratios and shear moduli, all listed here. So that's basically it. That's how you create a microstructure using MultiMech. Now, this is a pretty simple model. So we're going to take this a step further, and we're actually going to add a little more intricacy into this model. In this material, right here, seen right here, this was the porous adhesive. And we decided that representing this as linear elastic material isn't necessarily the best way. So we're going to represent it as a viscoelastic material. So let me open up a new MultiMech GUI dialog box. You see here, we created the porous microstructure through microstructure generation tool. And now we have only one matrix material. In this case, we want to use the viscoelastic material property. So we select that, and we have this whole list of different inputs that we can insert here. So it's a much more complex material you have and a lot more data you need. Thankfully, Multimechanics is very experienced in viscoelastic materials, and we actually have an in-house tool that can take DMA data and help you get these specific inputs. Once you select OK, we now have a more complex material. So it would be beneficial for us to actually run some virtual tests and see how this material responds, so we can feel out how the microstructure responds dependent on how we created it. So in this case, because it is a time-dependent material, we create 3 different strain rates, and we can run these different strain rates and observe the results. Now, thankfully, MultiMech has a tool that allows you to save all these different runs, which is located right here. And you can see that if you check this box, it'll save the copy after every run, and it'll save the inputs as well as the results. Furthermore, MultiMech also has a tool that compiles all these results into a single Excel file. So here we have the 3 different strain rates, and we see how the material responds. We see we have all the different components listed and available, and it plots them all together. Okay, now we've gone over a more advanced material. Now we're going to start showcasing the damage criteria that we can insert into this model. And the way we're going to showcase this is through the last RBE that we saw, the previous one, which was the unidirectional continuous fiber composite. You see here it's being loaded in the XX direction, and you can see how the fiber is bearing most of the load. So a few different ways that we can characterize damage in this model is, one, the fiber failure, the nonlinear effects of the matrix, and also any interface failure debonding occurring. So here's a materials tab that I've already generated with these different failure models. With the fiber, we can represent by inserting a failure model. And through this dialog, you can select a few different failure criteria, whether it's max principal stress or max principal strain, or something more complex like a Saïd-Wheeler-Hessian composite failure criteria. In this case, we go max principal strain, decide that we want to have stiffness reduction in elements and not just delete it. And now we can insert the different stresses in the tensile direction, compressive direction, and in shear. In shear, we have basically 1 to the e to the 20th because we don't want to characterize any shear failure here, so we set it to roughly infinity. And also, we have fibers that are inherently flawed, and the way generally that they represent this is through a Weibull distribution that governs the strength as a function of length down the fiber. Here you have the shape parameter and also the scaling parameter in the Weibull distribution. We'll show you how you can extract these different values later on in the webinar. Through the matrix, we can represent it as a continuum damage material. Here we have the standard linear elastic properties, and then you can put a damage law in here. We have a few different damage laws. In this case, we'll just go with Weibull, and again, we have the 2 Weibull parameters seen here. Finally, we have interface, and here we represent it the same way we represented fiber failure, except now we have obviously different values for the interfacial strength, and we don't want to represent it as a strength statistics. So that's interface failure, where we have one element around the fiber failing. What you also do is interface failure. What MultiMech does, we also have a automatic crack insertion algorithm that allows you to pick 2 materials, in this case, fiber and matrix, and we can designate an interface material. And what it does is when MultiMech notices that this criteria is reached, it'll automatically insert a crack into that. So you can actually simulate debonding through cracking. And here is the elastic contact we're using there to represent the cracking criteria. In this case, we're just going to use interface failure. So now that you've created a more complex microstructure with damage involved, you can now run different virtual tests. So when we run the virtual test in the 1-1 direction, which is the fiber direction, you can see the results in a Gmesh window. In this case, is seen right here. Notice that we have the RV that we're using, and we have the results queued up for the 1-1 direction. And when we run it, you can see the material start to load. And at the very end, you start seeing some of the fibers failing and degrading and transferring the load to other fibers. A better way to see that is through the failure status. So when we run it now, you can get to see when the actual elements fail, and you can kind of get a glimpse of the distribution of how stress will develop and how quickly your fiber will fail. Next, we can run in the 2-2 direction, which is dominated by the matrix and interface properties. So after we run this simulation, we can have another result window. We can pull up, and here we can run the stresses in the 2-2 direction. So as we see in the very end, it starts loading naturally, and then we start seeing some damage occur. Notice right here, there might be some debonding because all the load shifted away from the matrix. Therefore, it actually might be some debonding going around right here in this area. To validate that, we can go to failure status again. And when we run this, we actually see when the elements fail this direction. So like you saw, the elements are failing right around this region, which is where the stress distributions seem to fall in place. And if you remember in this case, we also have continual damage in the matrix. So when we run this, we actually see what kind of damage is accumulating within the matrix. See, at the very end, we have a decent amount of continual damage building up, which represents the nonlinearity in this matrix material.